Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we did talk about the magnetic field around a wireless. And of course, you do know that magnetic field is a vector quantity. That means it has both magnitude and direction. For the magnitude, we said for the magnitude of the magnetic field strength around a wire, we use the equation B, or magnetic field strength equals to mu naught I divided by 2 pi d. That is for the magnitude. What about for the direction? We said for the direction, we will use the right hand rule, yes? By basically aligning your or pointing your thumb in the same direction as the direction of the current, and then curling your finger, what represents basically the direction of the magnetic field around that wire. But remember this, the direction of the magnetic field at any point would be basically tangent to that circle, let's say, or tangent to that circle. And of course, we said there is an easy way to find the direction if you're given, for example, or asked to find the direction at a point, and that will be using, for example, the table where you have I, we have the point, and you have the direction of the magnetic field strength. And of course, we said if you're given a point, make sure that your thumb is aligned or it is in the same direction as the current. Then of course, you can straighten your hand, okay? On that point basically, then of course that would tell you the direction of the magnetic field, because basically once you are straightening your hand, let's say, that would be basically tangent to the circle, and that is how you can do that. And of course we did solve a few questions, and then we ended up, this was the last question that we solved, of course, and if you do remember, and then we ended up at question 2 here. Now, as for question 2, this is something very easy. It says the magnitude of the magnetic field at 10 centimeter is, listen, remember, whenever, or we're not allowed to use centimeter here, so we're going to convert this centimeter into meter, of course, and then after that we can plug this into the equation. So having 10 centimeter distance from a straight wire, we have the magnitude of the magnetic field strength is 2 times 10 to the power negative 5. That is Tesla. Remember this. Even if they don't tell you this, you should know this, that this is the magnetic field strength by the unit Tesla. The question says, calculate the intensity of the current in the wire given mu naught equals to 4 pi times 10 to the power negative 7. Okay, so let's solve this question as well, since this is also very easy, just the application of the equation. Right. That is not what I wanted. Okay, let's move this one aside a little bit so we can align it with this one here. Okay, so look at the information that is basically you're provided with. Okay, so we're given the distance, so let's write it down. Yes, the distance is basically equal to 10 centimeter. That is 0.1 meter, you can say, or just divide by 100. Okay, and then the magnetic field strength is at that point is basically 2 times 10 to the power negative 5 Tesla. That is this. Calculate the intensity of the current. So find the current. Okay, what is the current? If you know that mu naught is basically 4 pi times 10 to the power negative 7. Okay, having these information, you can find the current here. And of course now, so how are we going to do this? We do know the equation of the current. So B equals to what? B equals to mu naught I over what? Over 2 pi d. Remember that. Okay, we want I, so you can rearrange the equation, by the way. This one goes under, this one goes up. So I equals to what? I equals to, you can say B, right? That is magnetic field strength multiplied by 2 pi d divided by what? Divided by mu naught, sorry, because we're trying to find mu naught. We're trying to find the current, not mu naught. So divided by mu naught in here. Now all you need to do is just plug in the information, these numbers into the equation, you will be able to find this. So the magnetic field strength is basically 2 times 10 to the power negative 5, okay? And then multiplied by 2 pi times d, remember that is 0.1 meter. And then the mu naught over mu naught is basically 4 pi times 10 to the power negative 7. And of course we have 2 pi, and this 2 basically becomes 4, so this 2 cancel out. And this is basically 10 to the power 5 This is -7. It becomes what? How about we just do this one properly, and then of course let's get a calculator. Okay, let's take the calculator out. I can just take away this and show you the answer, but it would be best if we are doing it this way. So here we have 2 times 10 to the power -5. Excuse me. Okay, very good. And then here is going to be times 2 pi. Okay, and then what is next? That is basically 0.1, and then divided by 4 pi times 10 to the power -7, yes? So the answer to this question, of course, is going to be 10 ampere. Why 10 ampere? Because we have current, or we found current. So this is how you're going to find this. So basically in this question, you don't have to find or worry about the direction because they don't ask for that one. Okay, so moving next, we can say, what is next? Take a look at this question here. It says, this one is also very interesting. Okay, what does it say? It says a conductor is carrying a current is arranged so that electrons flow. Watch this. This is very interesting. Of course, this can be done 2 different ways, let's say. So a conductor carrying a current is arranged so that electrons flow in one segment from east to west. Now, you need to know, and of course, you already know this one, or at least most of you, remember this. Let me just move this one a little bit up. And then, of course, let's get some space to write a few things on. Okay, because what is the difference between this question and the previous one here? Whenever, let's say, if the current is, remember this, basically the current would be in the same direction as the, let's say, positive charges or protons here. So if the current is moving this way, let's just say the current is moving this way, the electrons would be moving in the other direction here. So remember this, guys, okay? The direction, if the direction of the current is this way, electrons is this way, then the current will be the other direction. In another, or to simplify this, we can say current will always be in the opposite direction of the electron movement or electron flow, let's say. If sometimes you might be given that, for example, the protons, let's say, moving to the right, that is, protons will be the same as the direction of the current. Or current will be given, let's say, current is to the right, that is fine. But whenever they give you the direction of the electrons, the current will always flow in the opposite direction here. So what is the direction that is given here? It tells you that the electrons are flowing from where? Let's do one more, make it smaller. Okay, it says, a conductor's current is arranged so that electrons flow in one segment from east to west, okay? So remember this, if this is the direction, north, south, east, and west, yeah? So watch this, electrons are flowing from where? From east to west. So if electrons are moving this way, what is the direction of the current? Remember this, guys, we said the direction of the current is always opposite to the direction of the electron. So if electrons are moving from east to west, that means the direction of the current is basically from west to east, or you can just say the direction of the current is basically towards east. That is all you need to know here. Okay, and then the next one here says, if a compass is held over this segment of the wire, in what direction is the needle deflect, okay? Hint, of course, recall that the current is defined as the motion of the positive charge. Of course, we've mentioned this one here. So remember this, if there is a current in the wire, there will be a magnetic field around this wire. Okay, let's draw this magnetic field perhaps a little bit more differently here. Let's say here's the direction of the magnetic field, okay? You could do one more, would be fine here. So we're trying to find, perhaps this one was extra. We're trying to find the direction of the current right, let's say, above the wire here. When we say above, in your perspective, by the way, okay? So if not, this is going to be above, but when we say above, that means right in front of the wire here. So in your perspective, let's say. So in this case, if that is the wire, let's say the current is moving this way. Once again, we said you can always straighten your hand. Let's say this is the direction of the current. Yeah, so you can see that it is from west to east or just in this direction. That is the case. When you do this, you're curling your hand is basically, that is the direction of the magnetic field. But what would be the direction of the magnetic field right at a point here? This, you can say right above at your perspective, to, let's say, to the wire here. If that is the case, we said as long as your thumb is pointing in the direction of the current, you can straighten your hand, your fingers. At that point, that would determine the direction of the current. So if I hold the compass right in front, let's say, or right above the wire, then of course the compass would point down, you can say, yes? So that would be the direction of the magnetic field right here. If not, you could just curl it up. At this point, you can make right angle or 90. So there are magnetic fields, circular magnetic fields, but remember the direction of the magnetic field at that point is always tangent to the circle. So imagine there is a circle here, and I'm just, let's say, sorry, that was unexpected. Okay, I think I was a little bit excited. So here's, let's say, the magnetic field, yes? If this is exactly what we're going to do. So here's, let's say, the wire. Okay, so we're trying to do this one here. This is the direction of the magnetic field. So the magnetic field direction at that point here is going to be tangent to the circle. So that is why I'm using a straight hand here, as long as your thumb is pointing in the correct direction here. So the direction of the magnetic field is going to be downward here. Or you can say if downward, if that is the case here, downward, of course, represents south, you can say using this one here. So if the direction is downward, this downward is going to be south in this case here, assuming that this is north, this is south, and of course, we have east and west here. Okay, that is for this one here. But look, what if we have, for example, what if the question were different, let's say? What if they were asking, for example, at a point behind the wire, let's say? So you can take a look at this compass here. Basically, this compass, that is where it points normally, yeah, when there is no magnet close by. This needle or the pointer or the red side basically pointing north, aligning itself with Earth's magnetic field. And of course, south, east, and west, yeah? So this is basically our case, which is right here, you can see. Okay, so if this compass is above the wire, you can say, then you can see that it is pointing downward, which is going to be south in this case here. Okay, that is this. What happens if we, for example, take the compass behind, let's say, the wire? So if this is the wire, we found the direction of the magnetic field at this point. What about the direction of the magnetic field at a point here? So once again, we said, always make sure that, by the way, your thumb is aligned with the same direction as the current here, so you can curl your finger here. Okay, so of course it's going to be something like this. But if I want to do it here, we're trying to find the direction of the magnetic field here. As long as, watch this, your thumb must be connected to the direction of the direction of the current so that it can get the correct direction here. So at a point behind the wire, let's say, in this case it is going to be upward in this case is going to be pointing north here. So if it is, this is how it goes, yeah? So at this point it is basically downward. If I go back or do, let's say, or find the direction behind, then of course it's going to be upward here. What if it is a direction, let's say at this point right here, is going to be outward, z direction, positive, yeah? And if it is below the direction here, if I do this, then of course, let's say a point below the wire, of course is going to be into the page, or you can say z negative here. Okay, so this question was also very interesting as well. You can do this one using the table, by the way, yes? So how are we going to, or can we do that using the table? We have the direction, you can say, of the current, and then here's what else is given, yeah? So this would be the direction of the magnetic field at this point there, or you can say at a point here, yes? The point is going to be on, let's say if that is above the wire here, is going to be towards z positive, yeah? So we have, let's say x positive, we have z positive, and then the other direction is going to be y negative. That is on x, y, z direction. If you're using, for example, the directions, let's say north, south, and all that, you know that this is towards east, yes? And then, of course, this magnetic field line is basically, it is right at a point, you can say, out of, above the wire, that is going to be out of this, yes? And then the direction of the magnetic field is going to be towards south, and that's it, okay? And here, more information about this, that is in two different cases. Okay, now, question 25. This question is also one of the interesting questions that we have here. By the way, this question, it might be confusing for some of you, but let's simplify this and make it easy here. But before that, we need to understand what the question wants, and then we can, of course, answer everything that they need in here. Okay, so what do we have in question 25? It says, let's move this up a little. Okay, take a look. It says two currents run in opposite directions in two parallel wires. So we have two wires. So these two wires basically, let's say this is one of them, That is one, and this is the other wire here. So 2 wires, and of course the current in each one of them is, let's say this is upward, and then the other one is downward here. That is the direction of the current, or I can do it here. So one of them is upward, the other one is downward. Okay, now 2 current in opposite direction is A and B. So let's call this one A and call this one B here. Okay, it says at a distance, so the distance between the two is basically 1 meter. Okay, if the current IA is a third of IB, what does a third of IB? You do know that, for example, when we say a third of, so we can say current A is basically a third. When we say a third, that means 1/3. A third of what? A third of IB. So we can say IA is basically equals to 1/3 or a third of IB. In another word, you can say the current in A is going to be weaker than the current in B here. Determine the position of the point along the line normal to the wire where the total magnetic field is 0. So at which point the net magnetic field is going to be 0 here. Now I want you focus at this point here. There's something very important. When 2 wires are in opposite direction here, remember this, the magnetic field inside, you can say, or in between the 2 wires is going to be, let's say, in the same direction. So of course, it's going to be positive, or you can say it is not 0 in this case, yeah? That is this. So the magnetic field basically is going to be 0 at one of the, or you can say the 2 sides here. So the magnetic field at a point here is going to be 0, and of course at a point here, it can be 0 as well. But now, why will it be 0? I'm saying that the magnetic field 0 around these is going to be, for example, 0, but not in between. Is there any reason behind this? The answer is yes. So, what is the direction of the magnetic field around this wire? And of course, we can find the direction of magnetic field around this too as well. Watch this. So, for this one here, the magnetic field is basically going downward, yes? If that is the case, then of course we can do this one here. You can see that the direction of the magnetic field is what? It is in this direction. Do you agree? Let me write it here. Okay, so let's go back one step. Let's use a different color so you can see. So the direction of the magnetic field, if that is the case, it is going to move like this, yes? So you can do it here as well. And of course, it's going to be this way. So on for this one as well. So for this wire, the direction of the magnetic field is this way. What about for this wire here? So for this wire here, the direction of the magnetic field is, or the direction of the current is upward. If that is the case, then watch this. Using your hand, the direction of the magnetic field for this one here is going to be this way as well. And you do know that when the direction of the magnetic fields are in the same direction, what do? We add them. So in this case, the direction of the magnetic field between the 2 wires is going to be additive, so it's not going to equal to 0. But guess what happens at the edges of this tree here? And of course, at a point here, you can say the magnetic field is 0 because this one is stronger, might not reach here, this one. But watch this. Let me redraw these 2 wires real quick one more time. So I'll just draw the magnetic field. This is for B, and this is for A. Watch this a little bit here. So we said the direction of the, what happens if I draw 3 lines? Because this one is stronger, so I'll draw 3 lines here. Okay, so we said here's the direction of the magnetic field of wire B, yes or no? You can see that, yes? Now, because the magnitude of the direction of, let's use black color here. What about the direction of the magnetic field of wire A here? So if this is wire A, it was supposed to be black. Where's, okay, yes. The direction of the magnetic field for A, watch this, guys, okay? Okay, so for A is going to be what? Is going to be in this direction here. But if you go like the other way here, because it's like concentric circles, yeah? You can see that these 2 are in opposite direction. I don't know if you can see that or not. Let's emphasize the difference here. Let's make red, and this one is nicer here. So you can see the direction is upward here. What about the direction for the black one here? We can use blue on this so that you can see the difference. Here it is. Oh, it is still black. It is downward, yeah? So we have 2 magnetic fields. One of them is upward, the other one is downward. So what will happen when we have 2 magnetic fields that are in opposite direction? Of course, they cancel one another out, but once they cancel one another out, then of course the magnetic field or the net magnetic field at this point here is going to be 0. You might say, Mr. What about the other side? Of course, the other side will be 0, but remember this one already has a weak magnetic field here. So it doesn't reach here. Of course, then of course we can say it is more likely at a point here the magnetic field will be 0 because it is, or the magnetic field for this one is weaker. Why not in between? Because at this point here the direction for both these are the same, so it is additive. It is not 0, but it is out of the lines here. So I hope you understood this one as well. But remember this. Okay, so we can say at a point here the direction of the magnetic field will be 0. Let's just say at a point here. You can name it any point here, okay? So now, as for this one here, but would it be this? We can say this point here, should have drawn it here, by the way. Let's make it right here. Okay, so let's use blue. So we can say the direction of the magnetic field at this point here, but what is the distance? Because we need distance, yeah? Because in order to calculate the strength of the magnetic field, you need the distance. So we don't know this distance because it is closer to A, so I can call this distance here, I can call it dA. Okay? Now, what about the distance from wire B? Okay? We don't know this distance, but we do know that the distance between these two wires is basically 1 meter. So can I say dB here? How can I do this? So let's say the distance from this point all the way to D, or all the way to B here, I can say dB equals to dA plus 1. Why dA plus 1? Because whatever is this distance here, basically, that is dA, okay? And then plus this distance, which is 1 here. So I can say the total distance is basically equal to 1 plus dA here. So remember what I have now, okay? We know that the magnetic field strength at this point is 0, that is 1. And we know that the distance from this point to wire A is called dA. And of course, the distance from this point to wire B, it is called what? It is called dB, but dB equals to what? Equals to this distance plus this distance. That is dA plus 1, so dB equals to dA plus 1 here. I hope it is not too messy. You can still find your way around here. Okay, so now let's erase a few things and do some calculations, yes? Okay. Let's make this one a little bit bigger so we can erase faster. Saving some time. Oh, I forgot. I should have not drawn this one. I'll write this one. Okay, so we said if that is the case at this point, B net must be 0. If that is the case, if B net is 0, what does it mean? That means the magnetic field strength for A must be equal to the magnetic field strength for B here. But we have wires, yeah? So in this case, what is the magnetic field for wire A? Of course, we'll say mu naught. That is basically I for wire A over what? Over 2 pi distance of A, let's say. And then for B here, of course, we have mu naught I for B, and then divided by 2 pi dB here. Okay, now take a look here because we have some common factors here. Mu naught and mu naught are the same. Of course, you can see that S. And 2 pi and 2 pi are the same, so these will cancel out. So what else do we have? Or what is left here? We can say IA over dA equals to what? Equals to IB over dB here. Okay, now, but remember this, guys. We said IA is basically equal to 1/3 of IB. So I can say 1/3, instead of IA, I'll just write this one. 1/3 of IB over what? Over dA. I don't know what is dA, but I'll just write it here. So, and then for IB, I'll just write IB and then divided by dB. But remember, we said dB equals to what? Equals to dA plus 1. Yes? Very good. Now I have dB and dB will cancel out again. You can use cross multiplication, or this 3 goes down, yeah? It becomes 1 over 3 dA equals to 1 over dA 1 over dA plus 1. Now, of course, you can use cross multiplication. So just use cross multiplication here. So it becomes what? 3 dA equals to dA plus 1 here, correct? Now we have 3 dA and this dA. This dA goes to the other side. Remember, we don't divide because there's a plus sign in between. So 3 dA minus this dA goes to the other side, it becomes minus. So minus dA equals to 1. 3 dA minus 1 dA, of course, we'll get 2 dA equals to 1 here. So now divide both sides by 2. So dA equals to what? 1 over 2, and that is 0.5. Very good. Now 0.5 what? Meter. Remember, so dA equals to what? Equals to 1 meter. So basically this distance, hope you can still see here. So this distance basically equals to 0.5 meter here. Now, if that is the case, then what is dB here? Okay, what is dB? Remember, we said dB equals to dA plus 1. So dB equals to 0.5 plus 1, 0.5 plus 1, of course, equal to 1.5. Let me just write this one nicer. Okay, so use blue. Okay, let's use blue. So, of course, now dA is basically, still not. All right, let's go back to this. We can erase this one, use a small eraser. Okay. Now, remember this. We're using dA, okay, plus 1. So dA was 0.5 plus 1. So now dB here basically equals to 1.5 meter. And that is basically the distance between, let's say, dB all the way to that point. Okay, all right, so that is how we can solve this question, by the way. Now, this question can be asked, of course, in a different way as well. What is the other way? Sometimes they might tell you, for example, let's say, what if, for example, we change the direction of the current? Now, this case will be different. Imagine this. Let's say, what would happen if the direction of the current in the two wires were in the same direction? Of course, in this case, will be exactly opposite to this. Let me see if I can give you an insight about what might or look, it might look like once they give you something different as this. So here's, let's say, one of the wire, and this the other wire. Let's separate them a little bit. Okay, that is one of the wire. The direction of the current, let's say it is downward here. The second wire, it is downward as well. This is A and this is B as well. So in this case, if the direction of the current between the two wires here, then of course the current inside or in between the two wires will be 0 here, or the magnetic field strength, the net of course. But the magnetic field strength here, let's say outside the wire, will not equal to 0 here. And of course, I can demonstrate this by using the right-hand rule. Let's say you would see that the direction of the magnetic field here in between the two wires will be opposite here. And if it is opposite, then of course, let's say one of them is upward, the other one is downward. If that is the case, then they cancel one another out. Then delta or net B, of course, is equal to 0. But at the two sides here, of course, they are going to be in the same direction and they will be additive here. If that is the case, how are we going to answer the question here? Once again, don't forget at which point, let's say at where exactly the magnetic field strength will be 0. Once again, because B is weaker, so of course it is going to be closer to A again. So we can say the whole distance is still 1 meter, by the way, okay? 1 meter. So we can call this one dA, and then the remaining distance, we can say what? dB equals to, we can say it is 1 minus dA. And how do we do that? For example, let's say the whole length is 3 meters. Let's just say, yes? Okay, so this is a point. You can call it x, yeah? So of course, we can call this distance x. We can call the remaining distance here, we can say 3 minus x, yeah? So whatever the x is, then this one here is going to be 3 minus x. And that is how it is. So we are basically use the same analogy to answer this question here. So once you are knowing this, of course, okay, what did I do? Let's see if we can go back to the next one. Yes, okay. So if that is the case, let's erase this one too. And then we can go back to this. So if that is the case, then of course I'm going to write the equation for you one more time. So we'll say in this case, that is basically current for, net current is going to be 0. That means BA is equal to B for wire B basically. In this case, mu naught I over 2 pi D. These are for A, and for A must equal to mu naught I for over 2 pi D. These are for wire B and wire B. But don't forget, these all will cancel out. These two will cancel out, of course. What is left? IA over DA then equals to IB over what? Over DB. But remember, we said DB equals to 1 minus DA. Okay, that is the remaining of this. And then, of course, you can substitute IA. Let's say we said IA equals to what? 1/3 of IB. So I'll do one more step for you. So it's going to be 1/3 of IB over DA equals to IB over 1 minus DA. And of course, these two will cancel out. Then do the math, which is going to be the same as the previous one. Then you will be able to find the answer here. Okay, that was very interesting as well. Take a look at these Rosati questions here. It says what? a wire carrying a current is arranged so that the electrons flow from one segment from west to east here. If that is the case, then make sure that if electrons are flowing from west to east, then make sure that current is basically flowing from east to west, or you can just say current is towards the towards west here, west, not east, west. If that is the case, remember this is the direction of the current. If a compass is held over this segment of the wire, in what direction is the needle deflected? So if the current is moving to, let's say to the west, if that is the case, so you can do this, okay? So if a compass is, let's say held over this, so here's the direction of the current, basically it's going to west. If we hold the compass right above the wire here, so which direction with the compass? Here's how your finger curl up, yeah? But tangent to the circle is going to be straight to this as long as your thumb is connected to the direction of the current. So in this case is going to point north, you can say, yeah? And of course that is B here, you can say. Okay, now as for question 2 says, it is the unit of the magnetic permeability of a vacuum, yes? So which one is the unit of magnetic permeability of a vacuum? Once again, if you forgot which one is the unit, just make sure that you know the equation for magnetic field strength of a wire, let's say, yeah? So of course we said B equals to, let's get this back. B equals to what? We can say, I think it is gone, yes, let's get it back. What is B equal to? Mu naught I over 2 pi ds. So mu naught, or B first, B equals to mu naught I over 2 pi d, yeah? So if you didn't know the unit, make this the subject. So mu naught equals to B times 2 pi d over the this one, over the current, yes? So this is basically Tesla. This is meter over the current, yeah? And so this is the unit for mu naught. Which one is Tesla meter over ampere? Of course, that is basically, which one is it? That is A, Tesla meter ampere. Okay, these are easy, of course, if you're not confusing yourself. Calculate the magnitude of the magnetic field at a point at a distance of this one, straight conducting wire DC if current this much. So that's just the application of the law. We've solved questions like this. Okay, now let's talk about magnetic field of a current loop. Okay, now in the previous, or so far, we've just been talking about the magnetic field around a wire. Okay, good. So let's take a look at the magnetic field around a loop in here. So just remember this, the magnetic field around a wire was mu naught I over what? Over 2 pi d. We said for the direction, thumb is basically, okay, is basically in the direction of the current. All right, what about fingers or curling fingers? Yeah, okay. Okay, feels like I forgot how to write fingers. Okay, okay, so fingers basically would be in the direction of what? Or curling finger, I can say. That would be the direction of the magnetic field strength, you can say. Okay, that is all for what? For a wire. Now we're going to talk about the direction and magnitude, let's say, for a coil, you can say. Or you can say a, like a loop, let's say. So if that is the case, what is a coil, by the way? Let's say we have a wire, something like this, let's say. You can start from this point, and then we can have something like this, yeah? So if you only consider this, that is basically a loop or a coil here. Or maybe we can do something, if I just draw a coil, that is going to be a coil here. And of course, now we can raise one part of this so that the wire can go into or out of this. We can have n turns of coil, of course. We can have 1 turn, it could be 2 turns, it could be 3 turns, it doesn't matter, yes? So this would be, let's say that is into, and of course this is out of 2. So this is basically, we have so many number of coils in this case as well. That is very messy here. So let me erase this using a bigger one. Okay. So how do we find, or what is a coil, guys? So basically this is a coil. If not, you could do more here. That is another coil. And of course it goes in, and of course here, let's say it goes into the coil, and this is out of the coil. This is the direction basically of the current into the coil. So how do you find the magnitude of the magnetic field strength around a coil, by the way? So the magnitude is going to be what? Is going to be mu naught, okay, Ni. Why Ni? Because we have numbers of turns basically. But most of the time N is going to be 1. Sometimes they just show you a loop, yeah? In that case, that is a single turn, you can say. And then divided by, remember this, we're going to find the magnitude of the magnetic field at the center of the coil. And of course, that is the radius, yeah? In that case, of course, we're going to use 2 times the radius. By the way, 2 times the radius, sometimes also, or you can call it diameter as well, because diameter, basically, let's use capital D for diameter, okay? It can be equal to 2. You could use D as well. It depends on what situation or what topic you're using here. This is not the density. Okay, diameter, let's say, equals to 2 times the radius as well, yes? So just in case if they gave you diameter, you can insert the diameter into the equation, but without the 2. Then in this case, instead of all this, you can just say mu naught Ni over the D, or the diameter, and that's totally fine. That is for the magnitude, yeah? What about for the direction here? How do we find the direction of the magnetic field around a coil in this case? Remember this. We're going to use the right-hand rule again, but there is one slight difference here. This time, we're going to point our fingers in the direction of the current. Your thumb would point the direction of the magnetic field, let's say. So, for example, if this is the direction of the current in the coil, let's say, we're going to align our hand or our fingers in the direction of the current. So you can see my thumb is pointing into the coil. So you can say the direction of the magnetic field is basically into the coil in here. Okay, so if that is the case here, so it is pointing this way. What if we reverse the direction of the current? What if the current were like this here? So if that is the case, let's say, then we could have said the direction of the magnetic field is basically out of the page here. And of course, if it is points, you do know that that means these are out of the page. But remember this, these, each one of these, you can say, form magnetic fields, you can say. And all these, of course, where there is magnetic field around the wire here, and each, you can say the magnetic field of each wire, because they are all in the same direction, will add up. And of course, we get different, or you can say a stronger magnetic field inside the coil here. Okay, so its weight is going to be stronger. The more turns you have or you add to the coil, the stronger the magnetic field for this one. So what are we learned so far in this case? Once again, we can find the direction and magnitude of the magnetic field strength in a coil. Using the magnitude, we'll say B equals to mu naught Ni divided by 2R. And then for the direction, we said your finger, or curling your finger in the same direction as the current, your thumb points the direction of the magnetic field in here. So this is basically the right-hand rule can be used to this. By the way, this is solenoid, you can say. But for a coil, this would be for a coil. So take a look about the magnetic field around the wire, you can say here, or around the coil. So each one of these magnetic field lines are going to be combined together to form something that is exactly like what? Like the magnetic field line of a bar magnet here. So of course, the more turns you add, the stronger the magnetic field will be, let's say. So, and you can see here inside the coil, the magnetic field lines are almost parallel to one another. So of course, stronger than the magnetic field lines are, let's say, out of the coil here. So if I have let's say 2 points, one of the points here, if I take 2 points, point A, which is out of the coil, and point B, it is inside the coil. Of course, point B would have a stronger magnetic field, because you can see inside this, the magnetic field lines are closer, it's almost uniform, you can say. So of course, it's going to be stronger than this one here. By increasing the number of turns, of course, this magnetic field strength is going to be increased. And the magnetic field lines of a coil, it is very similar to the magnetic field lines of a permanent or bar magnet here. So the magnetic field of a current loop is similar to B, which is a bar magnet here. So basically, this is a single coil, and this is a multiple coil, by the way. And if it is a coil like this, later on, we're going to call it solenoid, but just remember this. This is basically what we are talking about, so a coil. And more examples of coil you can see here. We have multiple or so many turns of coil, or you can see these are some other examples of coils here. And then these are basically coils. How do we find the magnitude of the coil? Let's say the magnitude of the magnetic field of a coil. Once again, B equals to mu naught Ni divided by 2R. So 2R, my bad, okay? So what does the magnitude of the magnetic field strength of a coil depends on? It depends on magnetic permeability, that is directly proportional. It depends on the number of turns, directly proportional. So by increasing the turns, the magnetic field strength increase. But depends on the strength of the current intensity, you can say. Stronger current produces stronger magnetic or more magnetic field, stronger magnetic field. Higher current, would be more proper to say this way, higher current produces stronger magnetic field strength around the coil. And then, of course, directly proportional with the radius of the coil. So the bigger the radius, the less the magnetic field strength here. And of course, we said mu naught represents the magnetic permeability of vacuum or air, and its value is basically 4 pi times 10 to the power -7. -7 what? We said Tesla meter divided by amperes. Okay, so B is measured in Tesla. Mu, we said it, and that is number of turns, so no unit, or just in turns, you can say. Current is measured in amperes, and then radius, or R, is basically measured in meter. All right, now we have a sample problem. Let's solve this question as well. Okay, so what do we have? It says along a straight, okay, I think it didn't work. Let's try it again. Okay, is it not working? I think it is not working. Okay. All right, so let's see. I think something's not right, but if not, we'll just zoom out this and see if we can do this one here. So let's do this one more time. Okay, let's see. I think it doesn't work. Okay, I'll just zoom out this so that we can avoid using this for now. What does it say? It says a long straight wire, okay, carries a current of intensity 6 ampere. Remember this. So basically we have two things here. We have a coil and we have a wire as well. Let me zoom in for a second before we zoom out again, okay? So take a look what we have. We have a coil, okay, that has a single loop, and of course we have a wire. And of course each one of these would produce a different magnetic field here. The question asks us to find the magnetic field right at the center of the coil. And how are we going to do this, by the way? Remember this. The wire, or the current in the wire, is moving upward, yes? Let's use this again. The direction of the current is upward here. So if I line my thumb in the direction of the current, you can see here, the magnetic field lines are going to be like this, yeah? So if I, like circles like this, and of course it's going to be this way, yeah? And if I do this way here, you can see that it is this way. And of course here is going to be this way as well. But do you remember we said how you can find the direction of, so this is the direction of the magnetic field here. Do you remember how we can find the direction of the magnetic field inside a coil? We said your fingers should be in the same direction as the current, then your thumb points to the direction of the magnetic field. So if that is the case, it is clockwise, you can see here, or counterclockwise. It is counterclockwise. So you can say if it is counterclockwise, the magnetic field is outside here. So you can see at a point here, the magnetic field line for this one, it is going into, but for a coil, it is going to out of, let's say, out of the coil here. So we have one of the magnetic field that is going into, and then one of them, or the other one, is going to out. So these two are in opposite direction. And if these are in opposite direction, what do you do? Of course, you're going to subtract them and see which one, for example, whatever that is left or remaining, of course, the magnetic or the final magnetic field is going to be in that direction. Okay, so let's zoom out this one, of course, and then we'll do more, or we'll solve the question and see how it is done here. So I'll perhaps do each part at a time or aside so you can see what it is. Okay, now, very good. So it says a long straight wire carries a current, intensity of this. So we have, for the wire, we have a current of, let's say, 6 amperes. Yes, very good. And that is amperes. It says where the part of this is bent into a circular loop. Remember, when it says a circular loop, that means we have a coil, but the number of turns for that coil is basically 1, okay? And one turn, let's say on one turn, that tells you one turn of radius, so we have a radius of 0.04 meter, as shown in the figure below. Calculate the magnitude of the magnetic field and its direction at the center of the loop here. So here's the loop. I'll draw the loop again. So here's the wire. Of course, here's the loop, and then goes like, this is not a perfect loop, but let's see if we can make this one better. So here's a wire. Okay, and here's, perhaps, let me make it nicer. So here's a wire. But if I draw a loop like this, and then we continue the wire, and then we erase this part. That's too big. Let's make it smaller. Perfect enough, I guess. So here's the loop. Okay, imagine if this wire were connected, yeah? Then, of course, like we said, the magnitude or the magnetic field for the wire, it is into, yes? And here's the center of the coil. By the way, this radius is going to be the same as for the wire as well, so you can call this one distance for the wire. For the coil, that is going to be the radius, which this two basically the same. So the distance we can say 0.04 meter. And then what else? The plane of the loop is basically coincide with the plane of the paper. Mu naught is equal to this much. So mu naught is 4 pi times 10 to the power negative 7. Okay, so how do you find the magnitude of the magnetic field for the wire? Okay, so for the wire here, equals to mu naught, remember this, I over 2 pi d, yes? So mu naught, you do know that, 4 pi, let's go back to this, 4 pi times 10 to the power negative 7, times the current that we have is basically 6 amperes, yes? Let's erase the amperes for now. And then divided by 2 pi times the distance, which is 0.04 meter. So what is the value for this one, by the way? We'll use a calculator, or the value for this one basically equals to what? Equals to 3 times 10 to the power negative 5 Tesla. What about the direction? Remember this, if that is the direction of the current, so it is going into, yeah? Remember, that is the direction, okay? You can say, or use at a point here, right at this point. So this point, you can use this, so at a point is going to be into the page here. Into the page, that is basically going to be Z negative. What about the magnitude for the coil? So once again, for the coil, is going to be what? B equal to mu naught Ni over what? 2 times the radius here. So that is basically 4 pi times 10 to the power negative 7 times how many, what is the number of turns? We said only 1, yeah? So multiply by 1, multiply by the current that is, the same current that is passing through the wire, yeah? Which is 6 ampere divided by 2 times the radius, which is 0.04. Double checking. Yes, okay, meter. So once you calculate all this, the magnetic field for the coil, it is going to be what? It's going to be 9.4 times 10 to the power negative 5. But what is the direction for the magnetic field for the coil? Once again, it is going clockwise, yeah? So if that is the case here, so your finger should curl up in the same direction as the current, your thumb points in the direction of the magnetic field, so it is outward, or you can say Z positive, yeah? Z positive. So that is the direction of the current. So we have two currents, two magnetic fields, as a matter of fact. One of them is out of the page, the other one is into the page. We're going to subtract them, yeah? And of course, the bigger one minus smaller one here, you can say. And that is exactly what we are being asked here. So we'll say delta B, okay, equals to, let's say, B2 or whatever, or bigger one actually, B2 minus B1. It doesn't matter which one is, we'll just say big minus small in this case. So we have 9.4 times 10 to the power negative 5. You can put this in a bracket, minus 3 times 10 to the power negative 5. And if that is the case, of course, 9.4 minus 3, that is going to be 6.4, correct? Okay, so I'll write the answer over there. So we can say delta B equals to 6.4 times 10 to the power negative 5, that is in Tesla. But remember this, because the magnetic field of a coil is bigger and the direction of the magnetic field of a coil was outside, so the you can say the what is this? The magnitude of the magnetic field is going to be out of the page.